So welcome to the stage, Abhishek Ebenezer, with his super exciting talk. Let's see, we'll wait for him to pop up.
Yeah, hello, Loxley. I've switched on my camera.
Hello, I can see you. That's welcome to the Global AI Student Conference. And
Thank you.
I've heard you have a super exciting talk coming up about optimal architecture for neural networks using bio-inspired algorithms. And I know I have a ton I need to learn this area, so I am super excited to hear from you. And so without further ado, feel free to start sharing your screen, and I'm very excited to learn more.
All right. I think the screen should be visible now. Just let me know, Loxley, when I can start.
It looks awesome.
Okay. So, hello, everybody. Welcome to the Global AI Conference. I hope you, so far, the sessions that you've watched, I hope you've enjoyed them. I was fortunate to watch some of the sessions that took part earlier. And it was really interesting to see how people presented projects on Azure Cognitive Services and the different machine learning services that are offered by Azure. And it was just so amazing to see that how, just from the comfort of our home and just using just very basic compute from our own home, we can access so much machine learning features of the highest efficiency and of the best quality that Microsoft has to offer. We can just use it for our own little projects, or even tomorrow when we have to build a website or an app, we can we can just use it in such an easy way. And it was really inspiring to see that. Today this session won't be about anything related to Azure. This is a research area that I have worked on for the past few months, and I can't wait to share about it with you guys. So it's about finding an optimal architecture for artificial neural networks. So, firstly, this is the roadmap that I thought we could use for this session. I'll give a brief about what a neuron is and how we can form a neural network from that. And then that will be pretty much brief. But I would like to talk more about why structure matters and why it's important to come up with an optimal architecture for a neural network. And also I'll be going through a bit of the past approaches that have been taken. And I'll take one old algorithm, which one that was invented in the 1990s, and another one that was invented fairly recently. So yeah, I just can't wait. I hope you guys enjoy the session, and yeah, let's go straight ahead. So so first I thought maybe if I could share a bit about why neural networks are important. So today neural networks, it's it's such a buzzword, and there's everyone's talking about it, and everyone wants to learn about it. Deep learning has become such an important part of our daily lives. So many lives depend on it for weather. You think about farmers across the world who use it for their crops, or you think about people who run their own businesses and how much they depend on it to increase their sales, and that it can offer a better service. So in so many ways, neural networks are important to us, and in a lot of ways, we're dependent on it. The main use of neural networks is because they're in our own brain, and our brain is basically this massive neural network that is performing so many computations every second, so that you can make the right perceptions and make the right decisions. So I just thought it would be before we move on, that it would be it would be really awesome if we could appreciate how important neural networks are, even just to our own lives. Right now, even as you're looking at the screen, there's so much text on the screen, and there's so much audio, and there's so much going on. And for your brain to understand that and to come up with the perception and to understand it, I think is something that happens so quickly without you even realizing that it's happening. And so that is something that's just fascinating, and I think it's very fortunate, and we should be really excited about the times we live in. So all this is possible in the brain because the brain has been wired to have the right architecture. So that's the beauty about it. that your brain has the exact perfect architecture that it requires to make all these complex decisions and all these complex computations, so that you can make the right decision in the quickest time possible. So so that's kind of like the intuition behind why this matters and why you need the best architecture for a neural network, so that today when we can go and apply neural networks to problems that are new and that come up every day, we need to know what is the best architecture so we can optimize, and so that we can make sure we can prevent any sort of underfitting or overfitting. So just to start off, I don't want to make this feel like a biology class, but I just wanted to point out a couple of things about a biological neuron before we can move further. So as you might already know, this is how a neuron looks. This is how the neurons in our body look. So so the dendrites are basically like the point of contact for the inputs, and then the body of the neuron sort of does the computations, and the terminals are sort of like the outputs. So and then the outputs, so the terminal is then connected to other dendrites of other neurons that are around this neuron, and it passes on information in a sort of in like a chain-like manner. So the outputs produced by this neuron are then passed to the next neuron, and then that neuron passes on information to the next neuron, and so that's how the information sort of flows through through a network. So the dendrites are used for the inputs, and you would have some computation happening as it travels through the neuron, and then you would have the outputs coming out of the terminals. So in a mathematical sense, it's been sort of converted into, in a very simple way, it's been converted into a sort of mathematical model. So just like how we had the dendrites for the inputs, here we just have input 0, input 1, input 2. So these would just be numbers. So these are basically, these could be anything. Maybe it could be pixels of an image, or it could be features that describe a certain feature of an object, or it could be just about anything. But so it would be basically, excuse me, it would be a number, and so basically you divide your inputs into different numbers, and you pass in each number through the inputs. And then you have weights. So weights are basically, they tell us how important the corresponding input is. So if you think maybe input 0 maybe is more important than input 2, then you would assign weight 0 to be much greater than weight 2. So they sort of tell us the relative importance of the inputs. So then a simple computation happens on the inputs. I won't go deep into it, but it's just a simple sum of the input and the weights, and then that's passed on to an activation function, which an activation function, I have a few resources for neural networks, and at the end of I'll mention them at the end of the video, but again, that's not a topic for this session. But just know that it's some sort of function where you just plug in an input, which in this case would be the sum of the input times the weight, and then we get an output. So that's how a neuron passes on information. It takes in the inputs, multiplies it by its own weights, takes the sum of it, passes it to an activation function, and that function returns us an output. So that's the basic functioning of how one neuron works. So there are many variants of this. There's even a perceptron and other basic models that try to mimic the working of a neuron. So please feel free to explore those. So coming to a neural network. So a neural network, you can build a neural network by assembling neurons together. Now, you could have so based on the number of inputs that you need to have and the number of outputs, you would have an input layer and an output layer, and then you would have a hidden layer. You could have one layer, you could have two, you could have 10 layers. Depending on the complexity of your problem, you could increase or decrease the number of hidden layers. So that would sort of help you perform more complex predictions or classifications that you're trying to solve. And so that's basically, so each node over here, as you can see on the right, each node represents one neuron. So as the input comes in, it also has outputs coming out of it, and each output would have a weight associated with it. So the outputs of one layer are fed as inputs for the next layer and so on. So it propagates like that through the entire network. I'm sorry, I have not been given enough time to explain how exactly a neural network works, but I promise I will show. I have a couple of links and I'll mention them at the end of the session. But yeah, I hope you can go back and look at how neural networks actually work. In case you don't know how neural networks work, it's okay. You can still follow, and yeah, I hope the remaining slides will be intuitive for you for the problem that we're trying to solve. So yeah, so this is now is probably like where the session starts now. So why structure matters. So if you had a data set and then maybe you wanted to make an image classifier, maybe you wanted to classify if an image contains a cat or not. So if you wanted to detect a cat, you would have an input layer first, and in the input layer you would have maybe the number of pixels that are there in the image or some features like that. And then you would have the output layer. The output layer might have one neuron, which is more like a binary value, like a 0 or 1. If it's 1, then maybe the image contains a cat, and if the output layer says it gives out a 0, then maybe your image does not contain a cat. So you're trying to train a neural network that gives the right zeros and ones corresponding to whether a cat exists in the image or not. So now for such a problem, you would create an input layer and an output layer, but you maybe will start with one hidden layer, and maybe with, let's say, 5 neurons in the hidden layer, and you would maybe train it, and you'll find that you'll get about 50% accuracy. And then maybe since you're not satisfied with that accuracy, you'll probably increase the number of neurons to maybe, let's say, 10 or 20, and then you find out that you've gone to 60% accuracy. And then you feel that that's not sufficient. You need to get like 95, 96, and you're still stuck at 60. So you'll add another layer. You'll add hidden layer 2, and then you realize you probably can get to 70% or something. So this takes a lot of time. Researchers today, they do spend a lot of time trying to figure out what the right configuration for the neural network is. And unfortunately, this is very time consuming. It's not optimal. You could end up using a very high number of neurons that you actually don't need, or you might be using a much lesser number of neurons than you're actually supposed to use, which could lead to some form of underfitting. So there needs to be a system or a mechanism to find out what is the exact number of layers I need and what is the exact number of neurons I need in each layer. So now it's not just what is the right structure, it's more about how many layers and how many neurons in each layer. So it's more like a variable dimension problem, where now you not only have to handle the complexities of how many layers do I need, but how many neurons in each layer. So if, for example, for classifying cats, if I require, let's say, 10 layers, I'm not going to get there if I start with just one layer, experiment with that, 2 layers, experiment with that, 3 layers. By the time I get to 10 layers, it's going to take a long time. So I need to create a system or a model that tells me for a given problem or for a given data set, I need to know what the right configuration is, and I need a model that can tell me that. So it's this area, it's widely known in deep learning that it's been a problem that has existed, and of late there has been much research in this area of trying to use different kinds of algorithms to solve this problem. People have used calculus like backpropagation and gradient descent, just like how they use it to train a neural network. They've even used it to to search a space and find the global minimum for that. So they've used calculus, but today I want to introduce some bio-inspired algorithms. Of late, these have gained much popularity because of the limitations of conventional mathematical methods, and so I would like to introduce a few of them. So before I move on to the bio-inspired algorithms, I just want to mention about, just put it in a visual form of what is the problem we're trying to solve. So if you just take the y-axis as our error and the x-axis as the number of neurons, we need to find now the exact number of neurons that we need for minimum error. So this is just a normal gradient descent method of trying to find the minimum. So basically the objective is that wherever we try to start on the graph, we're trying to find the lowest lying region. So for this example, there aren't any markings, but just for a visualization. So you can see the first point on the top left. So that's kind of where we start. That's like a random starting position. And now from there, we now need to find out where the global minimum is. So we need to find out which configuration of neurons can give us the least error. So we need to go all the way down to the bottom where we can't go to the bottom anymore. And basically that would end up, the corresponding point on the x-axis would end up giving us our best configuration. So this is just for one layer. And then if you extend this to two layers, you sort of get a 3D graph. So now you can see the problem is from getting from the top, we need to somehow find a way to get to that bottom, which is the minimum of the entire graph. So we'll have to get to the bottom of them. So you might have heard of different algorithms like backpropagation or gradient descent. These are great algorithms, and they work really fast and they're simple to implement. But sometimes in real life we have these kind of graphs, and so it's very easy to get stuck in a local minimum, whereas we need to find the global minimum. So it's just like a computer game where as soon as you start playing, you're just dropped at a random position, and now you need to collaborate with your teammates to find out like the right place, that exact one place which is the global best position. So backpropagation and the other kind of algorithms that are kind of old, they're great and they're really fast and simple to implement, but they tend to get stuck in local minimum. So bio-inspired algorithms recently have they are not 100%, they don't guarantee 100% success rate, but they do sort of like that they do sort of guarantee a better performance compared to backpropagation. So in real life, this is the kind of problem we're trying to solve. Wherever we are, like when we randomly start, we try to find our way through the terrain, and we need to now find a way to get to the global minimum. So these are some of the optimization algorithms that have been taken up in the past to solve this problem. So these are the bio-inspired approaches. So particle swarm optimization is basically its inspiration is taken from birds trying to search for food, and how as a group they can collaborate together, and just based on simple communication on who has the best position, they tend to converge together on the right place for food. So such behavior was displayed not only by birds but even by fishes trying to search for food, and these observations were made in a paper in 1995 by Kennedy and Eberhart. So they made and Eberhart, sorry. So they made these observations based on these animals on how they try to scavenge for food, and since then, particle swarm optimization has been one of the most popularly known bio-inspired algorithms. Bat optimization is another optimization algorithm inspired from the behavior of bats. There's also ant colony optimization that's inspired from colonies of ants trying to search for food. And then in the end, there's water wave optimization. So I'll be taking up particle swarm optimization and water wave optimization as the two algorithms. So particle swarm optimization was introduced in the 1990s, I think to be exact, 1995. And water wave optimization is a more recent algorithm. It's less than 10 years old, and I'll kind of just be briefing upon these two. So particle swarm optimization uses basically just two equations. I think I've got them here. Yeah. So it basically, if some of you know vectors, then you'll know that to completely define the motion of a particle, you need two kinds of vectors, which is position and velocity. So it just uses two equations to define a particle's position and a particle's velocity. And by particle here, I mean so so as you can see the black dot at the top, and then it tries to go to the global minimum. The black dot there is one particle. So later, as we would see, we would have multiple particles. And so the particle position and velocity are defined by these two equations. I won't go into the details of these equations. That's beyond the scope of this session. But it's just very too simple to implement equation. So it basically the velocity equation just involves the use of an individual best, which means what is the individual particle's best position so far, and then there is a global best. So every bird or every particle knows what their individual best position has been with respect to the food on the ground, and they also know what is the team's best position compared to the food on the ground. So they use these two parameters to sort of govern how they move and which direction they move and how fast they move in a particular direction. So that's basically how PSO kind of works. So the way I'll just probably go through one iteration of how the particles try to find out for the global minimum, or basically like the food on the ground. So there's something called a fitness function. So as you can see here, there's different shades of red, and dark red, the darkest shade of red represents the global best position. So that would be like the global minimum, and that's where we need our particles to reach. And so as you can see, there's a small red dot at the center of the graph, and then you can see the particles that they've been randomly initialized, and now they need to find their way. They need to find that global best position. So I'll just go through a single iteration of how PSO sort of governs the motion of these particles. So it just uses these two equations, and I'll just probably just run through these slides. And so as you can see, the position of the particles are just changing. And at one point, you can see that a group of particles have now assembled near the dark red dot. But there are also these group of particles that you can see below that have kind of like they found a nice position, but that isn't the global best position. That's maybe a local best position. So now they need to join the other particles that are near the global best, and they need to now they need to jump out of this local minimum and reach that global minimum. So this is where backpropagation stops. It can't really get itself out of a local minimum to reach the global minimum. But PSO and other bio-inspired algorithms have shown to display a nature where even though a large majority of particles can get stuck in a local minimum, they can still climb out and continue exploring and searching for a global minimum. So after a few more iterations, you can see that the particles are now all the particles converge to the global minimum. So this is kind of like a 2D representation. And basically, this diagram, as you can see, is like a top view of the same diagram over here. So this is how it would look in a 3D space, where the particles try to go through the terrain and continue, use those two equations, keep searching along with their peers, and then they try to find the global best solution. So it's a very simple algorithm to implement. Hope you guys can take it further and explore about it. So the last algorithm I have is water wave optimization. So basically, water wave optimization is based on a theory called water wave theory, and so it's basically about just like how water waves flow on near the ocean floor. So based on the wavelength of the water wave, you can sort of estimate how far from the ocean floor you are. So now on the ocean floor, you need to find the deepest point, and you can get to know that because of the wavelength of water at a particular height. And so they've used 3 mathematical equations to mimic the water waves and find out how far from the ocean floor you are. And so the more further you are from the actual solution, which is the global best. And the more closer you are, which means that once you have a shorter wave, then you would be more closer to the solution. So that's how you determine whether you're close to a solution or farther from the solution, just based on how you can, just based on the wavelength of water. So there's a lot of math involved. I think the paper is available publicly. Please check that out. It's a pretty huge algorithm. This is kind of like a more recent one. I think it was released in about 2015. So please feel free to explore. There are just so many different kinds of bio-inspired algorithms. Yeah, I just mentioned a few here, but it's by no means an exhaustive list. So please feel free to check that out. Yeah, so if you want to contact me further, this is my email if you want to discuss about research in this area. And if you'd like to give me feedback, please feel free to use the email ID. And below that is my LinkedIn. So that's it. I think I finished in my stipulated time of 25 minutes. I can take questions now. Would love to maybe take a couple of questions.
Yes, I am going to dive in some questions. First of all, what a fantastic talk. I learned so much from my end. So just a round of applause to you because I learned so much. I'm sure our entire audience learned so much. So the very first question, we actually have an amazing question for you.
Okay.
Be prepared. So our very first question is, so are any of the optimization algorithms you talked about implemented in any of the current frameworks like TensorFlow or PyTorch?
That's a good question. I am of them being part of any library as such, but I do know that various implementations of them exist in just raw Python, or so it probably already does exist in a framework like TensorFlow or PyTorch. I haven't used a library, but I have coded it myself. Other people have coded it themselves using Python or C. It's just available on a large scale on GitHub and on stuff like that. So yeah, this implementation is very basic. So even if you wanted to implement it, it's just a few like maybe just 20 or 30 lines of code. So yeah.
Wow, and that's a perfect segue into our next question for you. So yes, obviously this is the Global AI Student Conference. There's probably a bunch of beginners tuning in today. And so what would be the roadmap for this field? Like if I felt interested or if any of our audience felt interested in learning more, what would you say would be the best place for a beginner to start when learning this technology?
Okay, that's a good question because right now there isn't much material on trying to find an optimal architecture because that would require an in-depth study of the research papers and things like that because there isn't much textbook material for that topic. But there is quite a lot of material on bio-inspired algorithms and how they solve just engineering optimization problems in general. So you can find them on Udemy. There are a couple of courses. Just a quick search will give you a few. But I think the best place to learn the bio-inspired algorithms would be a research paper or something like that. So just probably using just Google Scholar, searching up the name of a particular bio-inspired algorithm, or just if you say bio-inspired algorithm, there's some really good papers that have done a review of all the bio-inspired algorithms and the ones which have been the best so far. So yeah, I would probably recommend research papers, but for a beginner, I think just trying to find out articles, people are talking about it on Quora, on different forums. It's a big problem. And so because there's so much to learn from nature and just trying to bring that into computers and trying to mimic the same behavior that other organisms exhibit in nature, I think is something that will fascinate anybody. And so it's really interesting and it's really fascinating. So I'm sure as a beginner trying to search by themselves, I'm sure they would gain a lot.
Yes, and I mean, I'm sure so many people are fascinated about this because I am so fascinated. That is what I'm doing after this conference. I'm going to read more about this and show it to all of my friends who are especially interested in nature and how this directly plays into some of the amazing AI solutions in place today. And so thank you so much for coming on. And so a quick note to our listeners, Avishai will be in our Global AI Cafe after his talk. So if you have any questions for him, like definitely go check him out, ask him questions. He's obviously a really smart guy, so definitely check him out, learn more about him. He can teach you so much because you're just, this has been an amazing talk. So thank you so much for coming on to the Global AI Student Conference.
Yeah, thank you everybody. Yeah, stay